2.6.3 Rotations. Rotations in n dimensions. The rotation group, so n, is the group of orientation-preserving linear maps of R to the n to itself that preserve the flat metric delta sub AB. Thus a rotation can be regarded as a tensor R sub B to the A on R to the n with one up and one down index, mapping vectors v to the A to rotated vectors v bar to the A equals R sub B to the AV to the B. In terms of the natural orthonormal frame for R to the n, the components are sub j to the I form and n times NA matrix satisfying.
See the equation, where R sub j raised to the ti power equals R sub I to the j. A matrix satisfying the above is called an orthogonal matrix, and the SON means the group of special orthogonal transformations of R to the n. Special means having determinant 1. The full orthogonal group, ON, is twice as large, including all reflections. A rotated vector has components v to the I equals R sub j to the IV to the j along the original basis, the set E sub I. The rotated vector is then. See the next equation. The last expression is what one would naturally write down if one began with the action of R on the basis vectors given by.
See the equation shown. To obtain, by linearity, its action on V. Rotations in two dimensions. The counterclockwise rotation by angle theta of a vector V in R squared is described by the above equation with the matrix. See equation 2-90. That is, see equation 2-91. The group has a single parameter, theta, which runs from 0 to 2 pi, and the same point is labeled by theta and 2 pi. Thus, the manifold of the group SO2 is a circle. Up to reparameterization, there is one path through the identity, namely theta goes to R sub j to the I of theta, and the corresponding tangent vector can be identified with the matrix.
See the equation. Thus, see equation 2-92. The Lie algebra is then the one-dimensional vector, R real, with a single Lie bracket, open bracket V, V close bracket equals 0. Equivalently, the structure constant tensor C sub BC to the A equals 0. Using the relation, epsilon sub k to the I epsilon sub j to the k equals delta sub j to the I, we can directly verify. Exponentiating a matrix in the Lie algebra gives back a one-parameter subgroup. Here there is only one parameter, and the subgroup is the whole group. See equation 2-93. The group SO2 is isomorphic to the group U, L, of 1 by 1 unitary matrices, that is, U, L, is the set E raised to the I theta power under ordinary multiplication. The isomorphism is simply R sub j to the I of theta goes to epsilon raised to the I theta power. There is another, larger group, that has an identical Lie algebra to that of SO2 equals U, 1, namely the group R of real numbers under addition. Again, because R is a one-dimensional group, its Lie algebra consists of the single element V tangent to the curve lambda goes to lambda through the identity at lambda equals 0. Two Lie groups with the same Lie algebra are locally isomorphic. A neighborhood of the identity of each group is isomorphic, but globally they are different. In this case R is a covering group of SO2 equals U, 1. It is a simply connected group and there is a homomorphism psi of R to SO2 equals U, 1.
See equation 2-94. The homomorphism wraps the line infinitely many times around the circle. Rotations in three dimensions. The counterclockwise rotation by angle theta about an axis along the unit vector n is described with matrix. See equation 2-95. Here n is a vector from the origin to any point on the unit sphere, and theta is any number between 0 and pi. We thus have a map from a ball of radius pi onto the rotation group, given by. See equation 2-96. Each point in the interior of the ball is mapped to a distinct point of the rotation group. Because a rotation by pi about n is the same as a rotation by pi about n, diametrically opposite points on the surface of the ball are mapped to the same rotation.
R of pi n equals R of negative pi n. See equation 2-97. The rotation group is therefore the manifold obtained from a 3-ball by identifying diametrically opposite points of its surface. This space is called Rp cubed, or real projective 3 space. Example 2.10. Consider the vector fields L sub x to the A, L sub y to the A, and L sub z to the A that generate rotations about the axis of R3. See the next equation. Find their commutation relations and check that L sub x commutes with L squared equals L sub x squared plus L sub y squared plus L sub z squared.
Solution. See the equations shown. If we use x equals x sub 1, y equals x sub 2, z equals x sub 3, then open bracket L sub x sub I. L sub x sub j close bracket equals negative L sub x sub k f of OR of ijk equals 123 and all cyclic permutations. Thus, see the equations shown.
2.6.4 SO 3 and SU 2. Euler angles. We need Euler angles primarily to describe the relation between SO 3 and SU 2 that underlies spinous. The relation belies the deeper meaning of Hamilton's discovery that multiplication in the rotation group can be written as multiplication of quaternions. We follow Goldstein's notation, but Goldstein likes to rotate coordinates instead of vectors. We will use the convention that a rotation is active, the motion of a vector. The components of a counterclockwise rotated vector relative to fixed coordinate axes are the same as the components of Goldstein's fixed, passive, vector relative to clockwise rotated axes. So Goldstein's clockwise matrices are our counterclockwise matrices. To get our formulas, change the sign of each angle in the formulas.
A rotation can be specified by what it does to an orthonormal frame, the set E sub I that starts aligned with the fixed frame I, j, k. The final location of E sub 3 can be specified by saying that it connects the origin to a point on the unit sphere with coordinates theta, phi. The other two frame vectors are then determined up to a rotation about E sub 3. Then an arbitrary frame orientation can be obtained in 3 steps. It can of course also be gotten by a single rotation about some axis. 1. Rotate through an angle psi about the z-axis r of psi k.
2. Rotate through angle theta about the x-axis r of theta I. 3. Rotate through angle phi about the z-axis r of phi k. Step I leaves E sub 3 fixed. Step, the second, rotates E sub 3 to a position in the yz plane at an angle theta from the z-axis. Step 3. Rotates E sub 3 to a final angle phi from the y-axis. The final frame E bar sub I is then given by. See equation 2-98. And any vector rotated by r sub j to the I of psi theta, phi, has components, along the fixed frame I, j, k. See equation 2-99.
Example 2.11. Examine the Lie algebra SO 3. See for further details. A. Show that the matrices k sub I, sub jk equals negative epsilon sub I jk satisfy the commutation relations open bracket k sub j. K sub k close bracket equals epsilon sub jk to the ik sub I. B. Show that. See the equation shown. And find the analogous. See the equation. C. Find the left invariant vector fields E sub 1, E sub 2, and E sub 3 at a point r of phi, theta, psi of SO 3, in terms of the vector's partial differential sign with over its sub theta, etc.
Solution. A. If k sub I, sub jk equals negative epsilon sub I jk, then see the next equation. And see the equation shown. Since epsilon sub 12 cube equals 1, epsilon sub 13 squared equals negative 1, and times epsilon sub 23 to the first equals 1, we see that. See the equation. B. See the next equation.
And since see the equation shown, we have see the equations shown. Similarly for see the equation and see the next equation.
C r of phi theta psi equals r of phi k sub 3 r of theta k sub 1 r of psi k sub 3, regarding a vector as a matrix. See the equations shown. So, see the equation shown. And r inverse of psi k sub 3, k sub 1 r of psi k sub 3 equals the 3 by 3 matrix row 1, column 1, 0 column 2, 0 column 3, negative sine psi row 2, column 1, 0 column 2, 0 column 3, negative cosine psi row 3, column 1, sine psi column 2, cosine psi column 3, 0 equals the cosine of psi k sub 1 minus the sine of psi k sub 2.
So, see the equations shown. Thus, see the equation, where E sub I of R is the left invariant vector field associated with E sub I of E equals K sub I. Similarly, we have see the next equation, and
see the equations shown.
see the equation shown. So, partial differential sign with over its sub psi equals E sub 3, see the equations shown, are grouped to give see the equations shown. Thus, E sub 1 plus I E sub 2 equals E raised to the negative I psi power partial differential sign with over its sub theta positive I E raised to the negative I psi power over sine theta times partial differential sign with over its sub phi negative cosine theta partial differential sign with over its sub psi. And E sub 3 equals partial differential sub psi. Example 2.12. Check that the vector fields above reproduce the Lie algebra of SO 3, e.g., verify that open bracket E sub j, E sub k close bracket equals epsilon sub jk to the I E sub I. See for further details. Solution. Starting with see the equations shown, we get
see the equations shown.
So, see the equation. Thus, see the next equation.